Hi, my name is Luciano Kadian, and I and Clement Vidal have been researching power density as a universal biosignature, an application to the Stellivore hypothesis. When looking for life in the universe, we're confronted with the Fermi paradox, which asks, where is everyone? Our traditional methods of looking for life usually look for something new, like Dyson spheres or big sorts of technology. However, what if we look back in our data and we could just be missing these signs of life? So the idea isn't that we need more data, but just a new metric for how to look on life. So we test mass-specific power density as that quantitative metric. And this is where binary stars and type 2 civilizations would come into play, because accreting binaries might be the ideal location for these civilizations because the rate of energy flow is so high that it's 40 times that of nuclear fusion found in main sequence stars, making it the most in the galaxy. So in an accreting binary, the compact object would be a neutron star, a black hole, or a white dwarf. And then the secondary object would be the star feeding into it, creating that high accretion, making it so valuable for such an advanced civilization since its energy flow is so high. And that's where the Stellivore idea comes in, that some of these systems may be advanced civilizations harnessing this energy. And since we already have mass and luminosity in our datasets, we can easily compute for power density, making it a perfect metric to try to find life in the universe. And now you might ask, why power density? Well, power density maps perfectly for biology because when we take the rate of energy flow given the amount of mass, biology fits very high on this graph, and then objects like a star and the Milky Way fit very low. Although the sun has lots and lots of energy, it has so much mass that its rate of energy flow is very low. So then we ask the question, where would these accreting binaries place? And what we found after sampling 130 white dwarfs, 30 neutron stars, and 19 black holes using young stellar objects as the control group is that these accreting binaries and supermassive black holes sit very high on the graph when looking for power density, right next to that of the biology plots, both being very far from equilibrium thermodynamics. And now you might say, well, a candle has very high power density, but a candle doesn't have a way to store and channel this energy like a civilization in a compact binary system would. And here we have our unified master graph where we plotted the biology data against the astrophysical data. And what we see is that the compact binaries and supermassive black holes rank just as high as biology does when we look at power density. And even if we look at the lower end of supermassive black hole masses, they still rank higher than all the young stellar objects, which was our control group. So this makes compact binaries and black holes a perfect location to start when we want to look for life in the universe. This makes mass-specific power density a perfect metric to start for when we want to look for life in the universe because it makes compact objects and biology sit at the same level on the graph. Although it can't determine life in the universe, it's a great start for when we want to look for life, as we could look at these accreting binaries and compact objects because we already have it in our data set. So the Fermi paradox might not be asking, where is everyone? But maybe it's more so, where is everyone in our data?